All right, so this is Math466, Advanced Applied Analysis, Lecture 24. What we're going to do today is we're going to continue our discussion of calculating the average moments. And after we finish calculating the average moments, we will have answers for what they are. And then the question will be, can we identify these? Does this look like the moments of any function? Given that I've said the word semicircle numerous times, you should probably be thinking, maybe it's the moments of a semicircular probability distribution. So the video from last time did not record, so any comments I may have said about the Yankees are sadly lost. So where were we? We were trying to compute the average kth moment. And so we ended up having a monstrosity, right? It equals 1 over 2 to the k, n to the k halves plus 1. The sum L1 goes from 1 to n, dot, dot, dot. The sum of Lk goes from 1 to n. Then we had the A, L1, L2, A, L2, L3, all the way up to A, L, K, L1. And then we hit this with the product 1 less than equal to j less than equal to I of P Aij Daij. So this is the long integral we need to evaluate. Fortunately, most of the integrals are going to be 1. There's on the order of n squared over 2 integrals, but we only have k variables, L1 through Lk in play. Oh, yeah. Thank you. Yeah, not nearly bad enough. Thank you. Excellent. Good. Now we have an integral. Oh, wait. The integral has to be inside the product. Right. So integral Aij goes from minus infinity to infinity. P Aij Daij. So we're choosing all of our elements. So P has mean 0, variance 1, finite higher moments. So because it has mean 0, we saw that, well, when we look at these, we can just collect them and see how many times do we have A11, how many times do we have A12, how many times do we have A13. If something is ever unmatched, because it has mean 0, it doesn't contribute. So no contribution from terms with something unmatched. And as it didn't record last time, I'm just making sure. All right, as of now, it says it's recording. OK. So we know everything has to be matched in at least pairs. And it's possible, of course, that something doesn't occur. So either it doesn't occur, or if it occurs in at least a pair. What we want to do now is we want to show that if you have a triple or more, it doesn't contribute. So this will be a lemma. No contribution if a triple match. Or higher. So that's going to enormously cut down on the possibilities. If we can prove this lemma, then the only way terms can contribute is if they matched in exactly pairs. And then you could have maybe 2 pairs are matched and another pair is matched, and they actually have the same value. It turns out that will also be a lower order term, and we won't have to worry about it. Yes?
What do you mean by matching?
So let's say we have A, L1, L2, A, L2, L3, A, L3, L4, A, L4, L5, A, L5, L6, A, L6, L7. Matching means L1, L2 is the same as either L3, L4, or L4, L3. It's a real symmetric matrix, so they have to have the same indices. So maybe this is A3, 5, A5, 7, or here, I wanted this to be, I'll match it with this one, A5, 7, A7, 3, A3, 5, A5, 7, A7, 5, and then I need actually L7, L1, A 5, and then 1 was 3. So if I look at this, I have 3, 5, 3, 5, and 3, 5. So those all get matched together. I have a 5, 7 twice. Nope, I have a 5, 7 3 times, and I have a 7, 3 once. So this term would be the same as A35 cubed, A57 cubed, A37. So would this term contribute? No, it wouldn't contribute because we have something unmatched. And because this is unmatched, when I now integrate this, it would be 0.
But if that was 2, wouldn't you still have, so what we're trying to show is that even if that was 2, you would still have
Correct.
no contribution.
No contribution. So for this one, it's not going to contribute because I have an A37. And so, is there any way to quickly fix this? We have a 3-7 all by itself.
So when you say like triple match, do you mean like?
I mean, 3 of the A's are the same.
Okay, so that also doesn't contribute because like A35 to the third.
Correct. It's going to be. It will contribute, but when you divide by n to the k halves plus 1, it will go to 0 in the limit. So this is enough to be 0 for all values of n, because it has mean 0. If you have a triple, the contribution in the limit will be 0 because of the high power of n you're dividing by. So when we have an expression like this, we can always take any expression, and we can write any expression as a11 to some power of L1 through Lk. I'll just write it as an L vector. And then we would have a12 to some power, all the way up to nn to some power. And so now, if I want to figure out what is the contribution of this, well, I now have to integrate against the p of aij daij. And so it's going to factor into a bunch of integrals. It'll factor into a product, 1 less than equal to j less than equal to I less than equal to n, of aij to the rij of L, p aij daij. But what is this integral? The expected value, the moment. Which moment? It's the rijth moment of our distribution P. So this would just be, we'll call it P rij of L. And then we would just have a product, 1 less than equal to j less than equal to I less than equal to n. So we can actually evaluate all these integrals. These integrals are just going to be products of moments. Then the question becomes, how many times do we have a configuration like this? So we have, n choices for L1, n choices for L2, n choices for L3, all the way up to n choices for Lk. We have n to the k tuples.
Quick question.
Yes.
Can we find any moment for any distribution?
Well, we're assuming all the higher moments are finite. So there's just some number for them.
Okay.
So we can call the rth moment just PR. That'll be just the integral of x to the r, p of x dx.
So we're not commenting on how you found it.
It's just some value, and it's finite. So we're just assuming that we have values like this. They're not infinite. So if we had the Cauchy distribution things would break down. And in the textbook, you'll recall the picture of the Cauchy distribution is very different in its behavior than the uniform and then the Gaussians. So the problem is we have n to the k tuples. If each tuple contributes, we're only dividing by n to the k halves plus 1. So the problem is this could explode. We need to show that most tuples don't contribute. And then we will deal with the ones that contribute. But if you give me a sequence of L's, I can then just collect common terms. A35 is the same as A53. I just see how many A11s do I have? How many A12s do I have? How many A13s do I have? And then the contribution of this will just be PRIL. Okay, now it comes down to counting. How many times as you go through the end of the k tuples do you have this? So how many times do you have this many A11s, this many A12s, this many A13s? Well, we know if anything is to the first power, its contribution is going to be 0, so we don't have to worry about it. So we only have to worry about tuples where everything is at least 2. And now the claim is that if even one of them is 3, there's so few such tuples. Okay? So this is the setup, and now we're going to go through the details. Okay, we ready? All right, this is where it gets a little annoying. Let's see. All right. So we want to show that if something is matched with the triple, it's not going to contribute in the limit. All right. Let's take as a first case maybe everything is matched in pairs and there's one triple. That's almost the best case. Well, let's think about what's going on. So here's A, L1, L2. Here's A, L2, L3. Here's A, L3, L4. Here's A, L4, L5. Here's A, L5, L6. I'll do maybe one more. A, L6, L7, all the way up to A, LK, L1. And now let's just match which ones are together. So maybe these two are the same value. And I'll draw a line connecting them if they're the same value. Maybe these two are the same value. Maybe this is also the same value as that. And then, other stuff of matchings in through here. So what does it mean for two things to be matched? It means either L1, L2 is the same as L4, L5, or L1, L2 is L5, L4. So if they're matched, once I specify these two indices, how many choices do I have here?
After they're matched?
After I specify L1, L2, and if I say it's matched with L4, L5, how many choices do I have for L4, L5? I have 2. And the important thing to note is that number of choices is independent of k, and it's more importantly, it's independent of n. For each of these matchings, once they're matched, I only have at most 2 choices for this. So if I think about L1 and L2 as free variables, are L4 and L5 free? No. I have at most 2 choices. I'm dividing by a huge power of n. I don't care about multiples of 2. As long as it's a bounded number of multiples of 2. I have at most k over 2 matchings. So I'll have at most 2 to the k halves. The number of powers of 2 I have will not be a function of n. I don't care about factors of 2. So L1 and L2 are free. Their match has 2 choices. So this is the first matching. Now it's possible I could have matched L1, L2 with L2, L3. Well, if I match it with L2, L3, then L3 has to equal L1.
And so the 2 choices are L1, L2, L2, L1?
Right, is that L4, L5 can either be L1, L2, or can be L2, L1. Then you have 2 choices. So here, L1 equals L4, and L2 equals L5, or L1 equals L5, and L2 equals L4. Those are the 2 possibilities. So in the first matching, we have 2 degrees of freedom, L1 and L2. So how many tuples do we have? Gives 2n squared tuples. Now this is the question of how much detail do we want to do in this class. All right, let's start going around. We now come to here. L2, L3 is matched with L3, L4. So in this case, L2 has already been specified from here. The L3s are the same. L3 is free, and L4 has to equal L2. So how many degrees of freedom do we get from this? we get 1 degree of freedom. Right? L3 is completely free, and then L4 has to equal L2. We could have instead maybe matched this all the way down over here. Well, if we had matched it down here, I erased a little bit too much. If we match it all the way down here, we've already specified L2. L3 is still free, and now these two numbers are fixed. So in the first matching, we had 2 degrees of freedom to start things off. In each subsequent matching, we only have 1 degree of freedom. And you just have to propagate this and go around and just do all the careful bookkeeping. Okay? So if you're adjacent, then L3 just lifts up and is free, and then L4 has to equal that. If not, this is matched with something down here, and now these two things are specified. And so each subsequent pair has 1 degree of freedom. Now in a situation like this, L2, L3 is now matched with L6, L7. So we would have 2 choices. So you would have at most, how many tuples? How many tuples would that give you? If this is matched down here. So in this case, we had 2n squared tuples. L1 and L2 were free, and I had 2 choices down here. Now these are matched. I only have 1 degree of freedom, and I have 2 choices down here. So how many tuples could I have maximum? 2n. So I have at most 2n tuples. So the best case for us is to have no triples or higher. Because now imagine we have a triple. L1, L2 is matched with L4, L5 is matched with L5, L6. These are specified. Once these are chosen, these are then specified, and these are specified. So I have another matching without getting a degree of freedom. So as soon as I have a triple matching, I'm not gaining as many degrees of freedom. Otherwise, every matching has 1 degree of freedom that it adds, which gives on the order of 2 and more tuples. If there's ever a triple,
What if it's not adjacent?
So if it's not adjacent, it wouldn't matter. No. If it's matched with, let's go to a L7, L8, if it's matched down here, once I have these matched, L4, L5 is now determined. And now L7, L8 is determined. It's either L4, L5 or L5, L4. So I could get an extra factor of 2, but I'm not going to get an order n. So it doesn't matter where the triple is. It only will increase the number of tuples by a factor of 2. Every time you have a new matching, you get a degree of freedom. So let's count how many tuples we could have. So best case, only pairs. The first one gives us 2n squared. And each subsequent one, what's the most it can give us? 2n. And how many such tuples do we have? So we go all the way up to k. So how many pairs could we have?
N minus 1 choose k.
If it's n minus 1 choose k, we're dead.
N minus 1 choose
We're dead if there's an n in it. How many pairs do we have? We have k objects that we're matching in pairs. How many pairs do we have?
k choose 2.
Not k. That's how many ways to match things into. How many pairs do we have?
K times k minus 1.
Oh, k squared.
We have k objects and we're putting them in
K divided by 2.
k divided by 2. Right? I have k objects. I want to put them into pairs of 2. How many pairs of 2 do I have? I will bring Cameron to class possibly on Friday to help. All right? And maybe I'll bring some dirt to eat. All right?
Circle.
I'm sorry?
Thinking something about like
Right. Now, if I want to know how many ways can I match things in pairs, now that's k choose 2. No, not quite. But so there are k halves pairs total. So this would be to the k halves minus 1.
But like you can take any of the k objects as your first two.
Right now, I'm not asking how many ways can I match things in pairs. I'm saying, given a matching, for fixed matching, how many pairs do I have? I have k over 2 pairs. The first pair gives me 2n squared degrees of freedom. Every subsequent pair gives me at most 2n tuples. So the number of tuples I have for fixed matching, this is for a fixed matching, is the following. Now you could ask, how many ways can I match things in pairs? That answer is independent of n. It's some function of k. It's k minus 1 double factorial. We'll talk about that in a moment. But it's independent of n. All I care about now is my independence. Well, okay, let's calculate this. This is going to be 2 to the blah. I don't care. I have n to the k halves minus 1, n squared. So I have n to the k halves plus 1. We are dividing by n to the k halves plus 1. If everything is matched in pairs, it's perfectly aligned so that your growth rate in n is exactly the same as what you're dividing by, and it has a chance of contributing. Now, this was an upper bound. Maybe we don't actually have this many tuples. But if things are matched in pairs, this is how many we will have. Now the question becomes, what happens if we have some triples or whatnot? Now here, in terms of how many pairs we have, we were assuming k was even. And I'm talking about k over 2. What if k is an odd number? Well, if k is an odd number, we have to have at least one triple. So the best case for us would be one triple and everything else doubles. So it would be...
And we couldn't have doubles in one single?
Well, if we had a single, we know it contributes 0.
Oh, okay,
So we're not considering that. So if k is odd, the best case would be 2n squared for the first one. And then because we have one triple, we'll have 2n, and it'll be k minus 1 over 2 minus 1. And this will be 2 to the blah, n to the k halves plus 1 minus a half plus a half. And notice the plus a half is less than the plus 1. So the contribution from the triples is going to be at most 1 over square root of n because all the integrals are finite. So this would show what happens if you have one triple and everything else doubles. Then you just have to go through all the possible cases. Well, what if I have two triples? What if I have a quadruple? What if I have a septuple? Well, there's only finitely many of them. We're matching things with k. And the number of such things is going to be a function of k. I don't care if it's k to the k to the k to the k. I don't care if it's k factorial to the k factorial to the k factorial to the k factorial. As long as it doesn't depend on n, when we let n go to infinity for a fixed k, it will be 0. This is one of the great things to learn from pure mathematics. How well do we need to bound something? How well do we need to understand something? All I need to know is I can isolate it so I have k dependence here and I have n dependence there. For whatever configuration I have, the number of such things to look at is a bad number of k. We could figure it out if we wanted to. If people want to, I'm happy to do so. It's just some function of k. Because it all comes down to how many ways can I match k objects in at least pairs. Well, if I'm matching things in at least pairs and I have k objects, it's some function of k. Big N can't come into play here. And then the best case is the more pairs I have, the more degrees of freedom I have. The more things that are matched together, the more I lose new degrees of freedom. So we see that the only chance we have to contribute is when everything is matched in pairs. If everything is matched in pairs, there's a chance. As soon as there's one triple, we're dead. It will be some crappy function of k divided by square root of n. So what this means is all the odd average moments are 0. Because with the odds, you have to have something either matched as a triple, or you have to have something unmatched. If something's unmatched, it integrates to 0. If something is matched in a triple, then your best case is you have something on the order of n to the k halves plus a half. You're dividing by n to the k halves plus 1. It's going to be 0. So we've reduced it to the case where everything is now matched in pairs. So is everybody mostly happy with this combinatorial analysis? Yes. Mostly is fine. Yes.
Could you just say why it gives 2n squared tuples? I feel like
So for the first one,
yeah.
both L1 and L2 are free indices. L1 ranges from 1 to n, L2 ranges from 1 to n. And now I match it with L4, L5. So if this is, say, this is A7, 3. Say I take L1 to be 7 and L2 to be 3. Then this has to either be A7, 3 or A3, 7. So I have two choices for the pair L4, L5 for one choice of L1, L2. I could actually have less than two choices. Imagine I chose A3, 3. Maybe I take L1 to equal L2. Well, then I would have only one choice down here. So the number of tuples from this first matching is at most 2n squared. It could be less, but it can't be more than 2n squared. Now that I know what L1 and L2 are, I've chosen L1 and L2. I have this beautiful sum of k things, each going from 1 to n. I've chosen L1, L2. I now move on here. L2 is already chosen. It's inherited from here. L3 is free, so I can choose L3 freely. This is now matched with something. So because they're matched, because I know both of these indices are now known. So L6 and L7 are now completely determined. So here, L4 and L5 were determined. L6 and L7 are now determined. I now continue moving and come over here. L3 is known. L4 is free. And so every time I have a pairing, the best I can do is to have a degree of freedom added. And the first one just gives me 2 because I get to choose both L1 and L2. In every subsequent one, some information is propagating and passing along. So we now don't have to worry about odd moments. We don't have to worry about anything not matched in pairs. Okay? So now this is going to become a chance to review some combinatorics. And we will eventually get back to something related to the Fibonacci numbers. So we've done some stuff with recurrences and Benford's law. The goal is to have a unified class. So we will actually return to recurrence relations. But we will return to a much harder recurrence relation than the Fibonacci's. You should be able to get to something a little bit better than Fibonacci's by the time you graduate. And so I want you to see how you handle recurrence relations like this. All right, so no contribution if a triple match or higher. So all odd moments vanish in the limit. I guess these are the all average odd moments. So for even matched in pairs. Now I could have one pair and I could have another pair, and maybe the indices are the same. If that's the same, then that's really a quadruple, and that doesn't contribute, and that will be lower order. So the first question to ask is, how many ways are there to match k objects in pairs? So now that we're calculating the moments, now we need to know, how this depends on k. So before, we were just trying to show which terms could contribute. And if all we care about is which terms could contribute, we don't care about the k dependence. That affects what the contribution is. Earlier, I don't care. I just want to know, does it have a chance to contribute? Now that I'm looking at the terms that have a chance to contribute, now I want to figure out what their value is. I don't think we did it in this class. Did we talk about the derivative of trig functions? Okay, this is a real brief aside, but the derivative of sine is much harder to calculate than the derivative of cosine at 0. And the reason is, what's the derivative of cosine at 0? It's 0. So if you're off by a multiplicative factor, it doesn't matter. So here's a quick, let's look at f of x equals sine squared x plus cosine squared x. also known as 1. Okay? Let's assume sine and cosine are differentiable functions. F prime of x is 2 sine x sine prime of x plus 2 cosine x cosine prime of x equals 0. If I now take x equals 0, I get 0 equals, what's the sign of 0? So I get 0 times sine prime of 0 plus 2 times cosine of 0 is 1 times cosine prime of 0. So we can immediately deduce that the derivative of cosine at 0 is 0. This equals 0. This is much harder. And all of differential trigonometry comes down to how do you take the derivative of sine at 0. So what you really want to do is you want to look at the limit as x goes to 0 of sine of x over x. Well, this is 0 over 0. How do we calculate, this limit? L'Hopital. Illegal. You cannot use L'Hopital to calculate the limit of sine of x over x. Why can you not L'Hopital it? So this is probably the most subtle mistake that almost everybody taking calculus will get. Why can't I use L'Hopital to get the limit of sine of x over x? I'm sorry? What's the derivative of x? What's the derivative of sine of x? How the hell do you know the derivative of sine of x is cosine of x? You calculate this limit, right? So if you want to use L'Hopital's rule to calculate this limit, you have to know this limit, and you have to know the derivative of sine is cosine. The derivative of sine is cosine only in radians. If you want to be truly annoying, you could do your trig functions in degrees. And now the derivatives of sine and cosine do not just go to each other with a sign change. You now have factors of 2 pi over 360. The whole point of using radians is so that this limit is now 1. This limit is non-zero. By adjusting my scale, by adjusting my units, I can make this limit 1. That's the point of radians. So it's a really subtle point, but it's a good point to know. And that's the real reason why we should use radians. This old stuff about 2 pi and pi, that's...
Wait, sorry. Is that limit related to the derivative of sine?
Yeah, because this is just, if you want, this is the limit as h goes to 0 of sine of 0 plus h minus the sine of 0 over h. And so it's really just sine prime of 0. So if we can understand this one limit, we can understand the derivative of every trig function. And you just use the angle addition formulas. So if people want it, I'm happy to do a digression on that. I want to make sure we get to at least a certain amount of the combinatorics of today so we don't have to split it on 2 days. All right, so let's go back to, here's the question. How many ways to match 2m objects in pairs? So here, I'm now assuming k equals 2m because we know k has to be even. So there's a lot of ways to do this. Probably one of my favorites is the following. 1, 2, 3, 2m minus 1, 2m. 1 has to be matched with something. How many ways are there to match 1 with something? 2m minus 1. So there's 2m minus 1 ways to match 1 with something. Now we look at the smallest unmatched number. How many ways are there to match that with something? 2m minus 3, because we've now lost 2 numbers. And now we look at the next smallest unmatched number. And you'll keep going all the way down until you get to 1. And so this is 2m minus 1 double factorial. The double factorial means every other. Okay, so another way to do this is basically to do it by induction. you assume this formula is, and you can verify this formula is true for small numbers, and then if you want to do it for 2m plus 2, well, I have 2m plus 1 ways of choosing what 1 is matched with. Now I have 2m objects left and by induction. So you can also do this by induction. There's another way you could do this. So let's see. One, two, three, 2m. Okay, so I want to try to do this the right wrong way. So okay, I need to choose 2 elements for my first pair. How many ways can I choose 2 elements for my first pair? 2m choose 2. Now how many ways can I choose my second pair? 2m minus 2 choose 2. All the way down to my last pair is now forced. So should that be an equivalent way of counting the number of ways to pair? I choose 2 elements, that's my first pair. I choose 2 more elements, that's my next pair. It's a really nice, subtle mistake.
You're not counting for like reshuffling pairs.
Yes, I'm saying this is now my first pair, this is now my second pair, this is now my third pair. I don't care which pair is which. So what do I have to divide this by? By m factorial. And so if you look at what goes on, this is 2m minus 1 over 2 times 2m minus 2, 2m minus 3 over 2, dot, 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 2 times 1 over 2. I have the m factorial. I'll put an m here, an m minus 1 here, all the way down to a 1 over here. The 2m cancels the 2m, the 2m minus 1 cancels the 2m minus 2, and you get 2m minus 1 double factorial. So this is another way to get this. How many ways, how many things do I have to look at? 2m minus 1 double factorial, or k halves minus 1 double factorial. You have seen this number 2m minus 1 double factorial before. Anybody remember where you've seen this? Or at least I know half of this class has seen this. Probably where? This equals the integral from minus infinity to infinity of x to the 2m, 1 over square root of 2 pi e to the negative x squared over 2 dx. The 2mth moment of the standard normal is 2m minus 1 double factorial. This is a really nice exercise to prove. Best way is probably to prove this by induction. Integrate by parts, write x to the 2m as x to the 2m minus 1 times x. Move one of the x's over here so that now you can integrate by parts. So it's a nice exercise, show that this is true. But there's a combinatorial significance to the moments of the Gaussian. Okay, I keep looking at the clock to see how much time is left. Okay. All right. So we now know how many ways there are to match things in pairs. The question now is, which of these matchings will contribute? But what's nice is we know that the average 2kth moment is going to be at most 2m minus 1 double factorial times the integral of the second moment, m times. What's the integral of the second moment? 1, because that's the variance. So we've just showed 2mth moment is at most 2m minus 1 double factorial. The only way it would be 2m minus 1 double factorial is if each matching in pairs contributes fully. If there are some matchings in pairs that do not contribute fully, then it will be smaller. Okay? But we've now bounded our distribution in some sense by the Gaussian. It turns out it's going to be very well bounded by the Gaussian. The semicircle has finite support. The Gaussian goes off to infinity. All right. So the textbook goes through, I think, the case where 2m equals 2. This is really not that bad of a case. A, L1, L2, A, L2, L1. I have to match things in pairs. I think I'll match them like this. L1 and L2 are completely free. It's always going to work. You'll get a contribution of 1. And so what you get for the average second moment, we'll have a 1 over 2. Now k is equal to 2m, which is 2 here. So we'll get 1 over 2 squared, 1 over n to the k halves plus 1. K halves is 1, so this is 1 over n squared. Then we have a sum. L1 goes from 1 to n. A sum, L2 goes from 1 to n. And each one of these is going to contribute 1 when I have AL1, L2 squared. And all the other ones will just be integrals of my probability density, which will be 1. So I have n squared divided by n squared, so I get 1/4. So we now know the average second moment is 1/4. And really, this power of 2 is coming from, in some sense, just adjusting the scale of x. It's coming from the fact that we're looking at the eigenvalues divided by 2 square roots of n. And that's where the 2 comes from. So really, the moments, it's actually going to be the moments of the Gaussian divided by 2 to the k, or 2 to the 2m. So we can do a little bit better, because we know those factors will still be there. All right, so this is the second moment. The second moment does not do a good job of showing how hard the problem becomes, right? If I want to match things in pairs and I only have 2 objects, this is not much of a challenge. It becomes more interesting once we now get up to 4 objects. So we have A, L1, L2, A, L2, L3, A, L3, L4, and A, L4, L1. How many ways are there to match these in pairs? Three. It's remember, it's supposed to be 4 minus 1 double factorial 3 times 1. So there should be 3 ways to match them in pairs. Can somebody give me one way to match in pairs? Okay, so one way is the cross. The other way, or the other 2 ways, are actually equivalent. So we could have, in the interest of time, I'm just going to write the pairs L1, L2, L2, L3, L3, L4, L4, L1. I could match like this. And this is the same L1, L2, L3, L4, L4, L1, L2, L3. Really, these 2 are equivalent. So let's look at the contribution from each of these matchings. In this matching, I choose L1 and L2. So L1 and L2 are free. As soon as I've chosen L1 and L2, what happens to L3? L3 is fixed. So L3 is fixed. What about L4?
Free.
So these have to be matched.
Is that L1?
That's L1, because remember I looped back. So what do we know about L4?
L3 is L1.
I'm sorry?
So L3 has to be
L3 has to be L1.
So L4 is free.
So L4 is free. L4 is free. And in fact, from over here, we knew L3 had to equal L1. Thank God it's the same thing over here. So if they were different, if they were forced to be different things, it wouldn't contribute. But L3 is forced to be L1. That's exactly what we need here. And now L4 is free, L1 is free, L2 is free. So we have 3 free variables. So what would we have for the contribution? We would have 1 over 2 to the k. K here is going to be 4. We would have 1 over n to the k halves plus 1. So k halves is 2 plus 1 is 3, so we'll have 1 over n cubed. Then we will have a sum L1, L2, L4 goes from 1 to n. And then all those will have contributions of 1. And so this will give us 1 over 16. Okay. There's a very small subtle thing which we should mention. What if L4 equals L2? Then this is a quadruple matching. And you will not get a second moment, you'll get a fourth moment. So technically, we actually need L4 does not equal L2. Because if we had L4 equals L2, it's a quadruple matching. Well, how likely is that? Of the n choices for L4, we have to stay away from one of them. So instead of getting n cubed over n cubed, we get n squared n minus 1 over n cubed 1 over 16. And as n goes to infinity, it's still 1/16. So when you look at this, as we go higher and higher and higher, we'll have to avoid a small number. But the number we have to avoid is independent of big N. It'll only depend on k, so in the limit it's not going to matter. So the goal here is to give you the broad brushstrokes and to convince you that if you cared enough to go through and do all the details, you could. But not to actually go through and do all the details. I want you to see enough because this is such a beautiful subject in terms of things it does. All right, so this contributes 1/16. This contributes 1/16. What about this over here? And then this will be a really, really good place to stop. So we have L1, L2 is matched with L3, L4. So L1, L2 has to be the same as L3, L4. And the next one, L1, L4, has to be the same as L2, L3. I'm sorry? Well, once I fix L1 and L2, then L3 and L4 are fixed. But this one might not be true. Right? So before, how many degrees of freedom did we have? We had n cubed degrees of freedom. Right? Before we had L1 and L2 were free, L4 was free. We had 3 degrees of freedom. Here, once I fix L1, L2, L3 and L4 are determined. So L1, L2 are free. It fixes L3 and L4, but this might actually violate. It may not be doable. Not all choices of L1 and L2 will actually work. Even if they did, however, this is only order n squared. And we divide by n cubed. So what's nice is I don't have to worry about whether or not, well, if I fix L1, L2, will there always be a choice of L3 and L4 that work? So here, well, I take L3 to be L1, I take L4 to be L2. Oh, that would work. So there should always be something that works. I actually don't care. I don't need to know that. Because from this point over here, I know I don't have 3 degrees of freedom. I only have 2. I have at most n squared tuples. And since I have at most n squared tuples, or maybe I have 2 because I could flip the order there. That's why I said on the order. I'm dividing by n cubed. There's no contribution. So admittedly, we don't have much of a data point, but given that class is about to end, what's different between these two cases? They don't have a common element. But just geometrically, when you look at the matchings, what's the difference between their structure?
You're matching adjacent pairs there, so you lose 1 degree of freedom, you gain 1 degree.
So here, each pair is contributing a degree of freedom, and the first pair contributes 2. Here, the first pair still contributes 2 degrees of freedom, but the next pair contributes none. Just structurally, when you look at these two, what's the difference between what goes on here and what goes on here? There's a cross. So this is the conjecture we need to end class on. If thou hath a cross, thou shalt get no contribution. Nothing. 1 cross is enough to kill all contributions. And so all we need to do is look at how many ways are there to match things without any crosses. So we're now going to get to review some combinatorics, and we'll see some generalizations of Fibonacci numbers. And so the question is, can we show that whenever you have 1 cross, you lose an extra degree of freedom? And what I love about these arguments is we are trying to be as crude as possible. We don't need to calculate what it is. We just need to show in the limit it's negligible. Think of it as the proof of the fundamental theorem of calculus. You just need to show this goes to 0, and then you take the limit, and then you have the formula you can work with. All right, so this is a really good place to stop.